700 million light-years from Earth, something impossible exists. A sphere of darkness so vast it could swallow billions of galaxies, but inside, almost nothing. Just 60 lonely galaxies drifting through 330 million light-years of empty space. Scientists call it the Bootes Void. Some call it the Great Nothing. We're about to journey into the largest mystery in the observable universe, where the laws of physics seem to break down, where time itself moves differently, and where something we can't yet understand might be hiding. In 1981, astronomer Robert Kirshner sat in his lab at the University of Michigan, staring at data that made no sense. He and his team were creating a three-dimensional map of the universe, measuring how fast galaxies moved away from Earth. It was routine work, tedious, even. They expected to see galaxies scattered everywhere, like stars in the night sky. Instead, they found something that shouldn't exist. A blank space appeared on their map. At first, Kirshner thought it was an error. Maybe the telescope malfunctioned. Maybe the data got corrupted. He checked again, then again. The blank space remained. It sat there like a wound in the fabric of space, 700 million light-years away, near the constellation Bootes. The team expanded their survey, adding more data points. The blank space grew larger and larger. They traced its boundaries, expecting to find galaxies filling in the gaps, but the gaps only widened. What they discovered was a roughly spherical region of space that contained almost nothing. They published their findings in a paper with a question mark in the title, as if they couldn't believe their own discovery. Other astronomers rushed to verify the results. Surely this was a mistake. Surely galaxies existed there, just hidden somehow. Survey after survey confirmed the truth. This region was real. It was enormous. And it was nearly empty. The astronomical community gave it a nickname that still sends chills down the spine: the Great Nothing. Kirshner's accidental discovery revealed a fundamental truth we had missed. The universe isn't spread out evenly. It has structure, it has holes, and some of those holes are so massive that they challenge everything we thought we understood about how galaxies form and distribute through space. Think about it. Every major discovery in astronomy happened because someone looked in the right place at the right time. Kirshner was just mapping galaxies. He wasn't searching for voids. He didn't even know voids of this scale could exist. But there it was, hiding in plain sight, waiting 46 years after Edwin Hubble first mapped distant galaxies. The discovery changed cosmology forever. It meant our models of the universe were incomplete. It meant something in the early universe created regions where matter simply refused to gather. Scientists started calling it a supervoid, a term reserved only for the most extreme examples of cosmic emptiness. But here's what keeps astronomers awake at night. The void didn't just appear in their data as an empty region. It appeared with boundaries so sharp, so defined, that it looked almost artificial, like something carved it out of space itself. And at the center, in a tube-like formation cutting through the middle, sat 60 galaxies that shouldn't be there. The question wasn't just what created the void. The question became, what's really inside it? 330 million light-years. Say that number out loud. Let it roll off your tongue. Now try to picture it. You can't. The human brain literally cannot comprehend distances this vast. But we need to try, because understanding the scale of the Bootes Void is understanding why it terrifies scientists. Light travels at 670 million miles per hour. At that speed, light from Earth would take 1 second to reach the Moon, 8 minutes to reach our nearest star after the Sun, 100,000 years to cross our entire galaxy. Now multiply that by 3,300. That's the diameter of the Bootes Void. Here's another way to picture it. Our entire Milky Way galaxy contains between 200 billion and 400 billion stars. The void could fit our galaxy inside it billions of times over, not thousands, not millions, billions. If you stacked galaxies like coins across the void's diameter, You would need to stack about 3,000 of them side by side. The void makes up roughly 2% of the entire observable universe. Think about that. 2% of everything we can see is just this one empty bubble. In a cosmos filled with trillions of galaxies, each containing billions of stars, each star potentially hosting planets, this region stands out as a monument to absence. Scientists calculated what should exist in a space this large. Based on the average distribution of galaxies throughout the universe, this volume should contain approximately 10,000 galaxies. Some estimates go even higher, suggesting up to 2,000 would be a conservative number. Instead, surveys have confirmed only 60 galaxies inside the entire structure. 60 out of 10,000. That's not just empty, that's impossibly empty. To understand how wrong this is, imagine walking through New York City and finding only 6 people in the entire metropolitan area. That's the level of emptiness we're talking about. The void isn't missing a few galaxies. It's missing 99% of what should be there. The void's volume has been calculated at 236,000 cubic megaparsecs. A megaparsec is 3.26 million light-years. Do the math and your brain starts to hurt. We're talking about a region of space so stupendously large that if you converted its volume to cubic miles, you would need a number with 38 zeros after it. 700 million light-years separate us from the void's nearest edge. That means when we observe it today, we're seeing it as it existed 700 million years ago, back when the first animals with spines were crawling onto land on Earth. The light from those 60 lonely galaxies has been traveling through absolute darkness for longer than complex life has existed on our planet. The void makes the empty space between galaxies look crowded. In normal regions of the universe, galaxies sit a few million light-years apart. In the void, you might travel 10 million light-years before encountering a single galaxy. Imagine being an astronaut drifting through that darkness, knowing the next island of light and matter sits 10 million light-years away. But the scale isn't even the strangest part. What's strange is the shape. 60 galaxies. That's it. That's all we found. In a region that should blaze with thousands of galactic cities, we've discovered only 60 lonely islands scattered through an ocean of nothing. This isn't just unusual. According to our best models of how the universe works, this is borderline impossible. When astronomers first swept the void with their instruments, they found 8 galaxies. Just 8. They thought maybe their equipment wasn't sensitive enough. They upgraded their telescopes, expanded their surveys, and spent years searching. Decades of observation have brought the total to 60. That's where the count sits today, and it's not going up. Here's the paradox that breaks cosmology. The universe started with matter distributed relatively evenly. Sure, there were tiny variations, quantum fluctuations in density, but nothing that would explain gaps this enormous. Gravity pulls matter together. That's what it does. That's all it does. Over 13.8 billion years, gravity has been clumping matter into stars, galaxies, and clusters. Where gravity pulls strongly, matter gathers. Where it pulls weakly, matter drifts away slowly. But it doesn't just vanish. Those 60 galaxies prove that matter did exist in this region once. Something either pulled it out or prevented it from gathering in the first place. Neither explanation fits our physics. Computer simulations have tried to recreate the void. Scientists input the known conditions of the early universe and let virtual physics run forward in time. The simulations produce voids. Yes, small ones, medium ones, even large ones measuring 50 to 100 million light-years across. But nothing approaching the Bootes void scale forms naturally in the time available since the Big Bang. The math simply doesn't work. For gravity alone to create a void this size, you would need roughly twice the age of the universe. It's like finding a canyon on Earth that would take 2 million years of erosion to form, except Earth is only 1 million years old. The feature exists, but it shouldn't. Those 60 galaxies make the paradox worse. They're not randomly scattered throughout the void. They're arranged in a rough cylindrical structure, a tube cutting through the center of the sphere. It's as if they mark the boundary where two smaller voids touched and merged, but even that theory has problems. If two voids merged, we should see evidence of that collision. Galaxies should be getting pulled toward the edges, leaving the center completely empty. Instead, those 60 galaxies seem frozen in place, trapped inside a structure that logic says they should have escaped from billions of years ago. Some of these void galaxies are spiral galaxies, pristine and undisturbed. They look exactly like galaxies in dense regions, just isolated. If they formed in near-perfect isolation, away from gravitational disruption, they should look different, more primitive, less evolved, but they don't. They look normal, which makes their location deeply abnormal. Astronomer Greg Aldering said something haunting about the void. If our Milky Way sat at its center, we wouldn't have discovered other galaxies existed until the 1960s. Think about that. Human civilization would have developed believing our galaxy was the entire universe. Our telescopes would peer out and see nothing but darkness in every direction. We would have been alone, completely, utterly alone, until one day we built a telescope powerful enough to spot the faint glow of another galaxy, hundreds of millions of light years away. Can you imagine that revelation? That shock? But we don't live in the void. We live in a cosmic metropolis. And somewhere out there, in the great nothing, on a planet orbiting a star in one of those 60 galaxies, someone might be having that exact revelation right now. Or maybe the void isn't as empty as we think. Close your eyes and picture the night sky, the Big Dipper, Orion's belt, the misty band of the Milky Way stretching overhead, thousands of stars visible to the naked eye. Now erase them. All of them. That's what the night sky would look like if Earth formed in the center of the Bootes void. Absolute darkness. Pure, unbroken black. No constellations. No shooting stars. No planets except the ones in our own solar system. Just our star. Maybe a few neighbors, a few dozen light years away, and then nothing for millions of light years in every direction. The night wouldn't just be dark. It would be empty in a way that would fundamentally reshape human psychology. Ancient humans navigated by the stars. They created mythology around constellations. They tracked seasons, predicted floods, and guided ships across oceans using the predictable patterns of the heavens. In the void, none of that would exist. The sky would teach us nothing except that we were alone. Philosophers would have developed entirely different worldviews. The question wouldn't be whether other worlds existed out there among the stars. The question would be whether anything existed beyond our immediate neighborhood at all. Religion, science, art, everything would be filtered through the lens of cosmic isolation. When Galileo pointed his telescope at the sky in 1610, he discovered Jupiter's moons and revolutionized human understanding. In the void, Galileo would have pointed his telescope into the darkness and seen more darkness. The scientific revolution might have taken centuries longer, or never happened at all, because there would be nothing to observe that challenged existing beliefs. It took humanity until 1924 to confirm that other galaxies existed beyond our own. Edwin Hubble used the 100-inch telescope at Mount Wilson to resolve individual stars in the Andromeda Galaxy. If we lived in the void center, Hubble's telescope wouldn't have been powerful enough. Not even close. He would have seen nothing. We wouldn't have discovered other galaxies until the 1960s, when technology finally advanced enough to detect the faint, distant glow of galaxies hundreds of millions of light years away. Think about that timeline. Humanity would have split the atom, developed computers, and sent humans to space, while still believing our galaxy was the entire universe. The Copernican revolution taught us we're not at the center of anything. Earth orbits the star. Our star is one of billions in the galaxy. Our galaxy is one of trillions in the universe. But in the void, we would be at the center of nothing. That knowledge would either crush us or make us believe we were uniquely special. Children growing up in the void would never point at the night sky and ask about other worlds. They would ask why the sky is empty. why we're alone, whether we're living in the corpse of a universe that died long ago. The psychological impact of that isolation would be profound and inescapable. Our entire understanding of the universe comes from observing it. In the void, there would be almost nothing to observe. Cosmology as a science would barely exist. We would know our galaxy, maybe a handful of distant neighbors, visible as tiny smudges of light, and that would be it. Our theories about the Big Bang, dark matter, and cosmic expansion would take centuries longer to develop. But here's the truly disturbing part. We would eventually build powerful enough telescopes to see beyond the void. And when we finally detected the walls, those massive superclusters of galaxies surrounding us in every direction, we would realize we're inside something, trapped inside a bubble, and we would have no idea how or why. That moment of discovery would redefine everything we believed about our place in the cosmos. And in the real universe, in the normal, galaxy-rich regions where we actually live, scientists looking at the void are having that exact same revelation in reverse. We're outside looking in, wondering what it means. The universe has a structure, not a random scatter of galaxies flung in every direction, but an organized pattern that looks almost biological under the right instruments. Scientists call it the cosmic web, and once you see it, you can't unsee it. Picture a three-dimensional spider web stretching across billions of light years. Thick strands of galaxies wind through space, connecting at massive nodes where thousands of galaxies cluster together. Between the strands sit empty regions, bubbles of low density where almost nothing exists. This is the fundamental architecture of reality, and the Bootes void represents a tear in that web so large it shouldn't be possible. The web formed in the first few 100 million years after the Big Bang. Matter wasn't distributed perfectly evenly. Tiny quantum fluctuations created regions slightly denser than others. Those denser regions had stronger gravity. They pulled in more matter. That matter increased their gravity further. A feedback loop began, and it hasn't stopped for 13.8 billion years. Over time, matter collected along the paths of strongest gravitational pull. These became filaments, massive strands containing thousands of galaxies each. Where multiple filaments intersected, superclusters formed, the largest gravitationally bound structures in the universe. And between the filaments, voids emerged as matter got pulled away toward denser regions. This process created voids throughout the universe, lots of them. In fact, voids make up roughly 80% of the universe's volume. Most measure 30 to 300 million light-years across. They're empty, sure, but not completely. A typical void still contains some galaxies scattered throughout. The cosmic web has holes, but it's still connected. The Bootes void breaks this pattern. It doesn't just represent a gap between filaments, it represents a complete absence of web structure. Imagine a spider web where someone cut out a circular section, leaving frayed edges but nothing in the middle. That's what we're seeing. 5 massive structures surround the void like walls. The Ursa Major supercluster, the Shapley supercluster, the Hercules supercluster, the Corona Borealis supercluster, and the Bootes supercluster itself. These aren't small groupings. Each contains thousands of galaxies packed relatively close together. They form a nearly perfect sphere around the void, as if they're defining its boundaries. Here's what makes astronomers uncomfortable. The void's spherical shape is too perfect. Natural voids form from gravitational processes that should create irregular shapes. Matter gets pulled unevenly. Filaments intersect at random angles. The resulting voids should be lumpy, elongated, misshapen. But the Bootes void is nearly spherical, with those 5 superclusters marking its perimeter like points on a geometric figure. Some scientists propose that the void formed from multiple smaller voids merging together. As the universe expanded, these smaller bubbles touched, combined, and created one massive structure. That theory explains the rough tube of 60 galaxies cutting through the center, marking where the smaller voids made contact. But the merger theory has problems. When bubbles merge, they don't form perfect spheres. They form irregular shapes with obvious seams. The Bootes void shows no clear seams. Its boundaries are smooth, defined by the surrounding superclusters in a way that seems almost intentional. The cosmic web should have healed this wound by now. Gravity should have pulled galaxies into the void over billions of years. Instead, the void appears to be growing. As the universe expands, driven by dark energy, the void expands with it. The web doesn't heal, it tears further. Filaments in normal regions of the universe run in curved, winding paths. They bend around dense regions, following the complex gravitational landscape. But near the void, something else happens. The filaments approach the boundary and stop. They don't curve around it smoothly. They terminate, as if they hit an invisible wall. Scientists have studied the velocity of galaxies near the void's edge. These galaxies aren't falling into the void to fill it. They're moving away from it, pushed by the expansion of space itself. The void isn't just empty. It's actively becoming more empty over time, pushed apart by forces we barely understand. The cosmic web reveals the skeleton of the universe, and the Bootes void reveals something wrong with that skeleton. Perfect spheres don't exist in nature. Planets aren't perfect spheres. They bulge at the equator from rotation. Stars aren't perfect spheres. They have magnetic fields, surface activity, and gravity variations. Even bubbles, floating through the air, wobble and distort as they drift. Perfect spheres are mathematical abstractions, not physical realities. The Bootes void is almost perfectly spherical. That shouldn't be possible. When astronomers mapped the void's boundaries, they expected to find an irregular shape. Gravitational processes create chaos. Matter clumps unevenly. Forces pull in different directions at different strengths. The result should be a void with lobes, extensions, and asymmetric features. Instead, they found something that looked designed. The void measures roughly 330 million light-years across in every direction, not 300 million one way and 400 million another, roughly the same in all directions, centered on a specific point in space. That level of symmetry demands an explanation, and none of the standard explanations work. Gravity creates structure through collapse and accumulation. Dense regions attract matter, becoming denser. Sparse regions lose matter, becoming sparser. This process should create elongated voids stretched along the directions where filaments pulled matter away most strongly. The Bootes void shows no such elongation. It's round like a bubble, but bubbles in space don't work like bubbles in air. Some researchers proposed that the void formed from an explosion in the early universe, a massive release of energy that pushed matter outward in all directions, creating a spherical empty region. But explosions that large would leave evidence. We would detect temperature variations in the cosmic microwave background. We would see galaxies at the void's edge moving at unusual velocities, still carrying energy from the initial blast. We see neither. The sphere's symmetry suggests a central point, something at the very heart of the void that either pushed matter away or prevented it from gathering in the first place. Scientists have aimed instruments at that central region, searching for anything unusual: black holes, dense matter concentrations, exotic particles. They found nothing. Well, almost nothing. The tube of 60 galaxies runs through that central region, but even those galaxies seem arranged more precisely than random chance would allow. They form a cylinder, not a sphere, a one-dimensional structure cutting through a three-dimensional void. That geometry raises questions nobody can answer. If multiple smaller voids merge to create the Bootes void, the result should show clear evidence of that merger. Imagine two soap bubbles combining. At the moment of contact, they form a shared wall between them. That wall eventually disappears, creating one larger bubble, but the process takes time and creates temporary asymmetries. The Bootes void shows no sign of this. No internal walls, no remnant structures, just smooth, uniform emptiness. The surrounding superclusters define the sphere's boundaries. 5 massive structures, each containing thousands of galaxies, positioned at roughly equal distances from the void's center. They form a polyhedron around the emptiness, like vertices on a geometric solid. That arrangement suggests coordination, but coordination requires a mechanism. Natural structures can create approximate spheres through balanced forces. Stars are roughly spherical because gravity pulls equally in all directions, but the void is empty. There's no central mass creating symmetric gravitational pull. Instead, we have the opposite, a symmetric absence of mass. Physicists have proposed that the void represents a region where dark energy dominates more strongly than elsewhere. Dark energy pushes space apart, working against gravity's pull. If dark energy were somehow concentrated or more active in this region, it could prevent matter from accumulating and push existing matter away. But dark energy should be uniform throughout the universe. Why would it concentrate here? Another theory suggests the void marks a region where the fundamental constants of physics vary slightly from the rest of the universe. If gravity were fractionally weaker there, matter wouldn't clump as efficiently. Over billions of years, that tiny difference could create a massive void. But we have no evidence that physical constants vary by location. The sphere's perfection haunts researchers because it implies intent or design where only natural processes should exist. And in physics, when something looks designed, it usually means we're missing a crucial piece of the puzzle. The question isn't just why the void is empty. The question is why it's so perfectly empty. Here's where the Bootes void stops being just weird and becomes genuinely impossible. The universe is 13.8 billion years old. That's confirmed. That's solid. We know this from multiple independent measurements. The void is 330 million light-years across. We know this too. Do the math, and nothing adds up. Gravity moves slowly. It's the weakest of the 4 fundamental forces, and it operates over vast distances with agonizing patience. To create a void, gravity must pull matter away from one region and concentrate it in another. That process takes time, lots of time, more time than the universe has existed. Scientists have run the numbers repeatedly. They've used supercomputers to simulate how voids form from the conditions present after the Big Bang. They input the known distribution of matter, the strength of gravity, the expansion rate of the universe. They let the simulation run forward 13.8 billion virtual years. Voids form in these simulations. Small ones appear quickly. Medium ones take longer. Large ones, measuring 100 to 200 million light-years across, emerge eventually. The Bootes void doesn't emerge. Not in 13.8 billion years. Not even close. To create a void this size through gravitational processes alone, you need roughly 25 to 30 billion years, maybe more. The universe isn't old enough for this structure to exist naturally. Think about what that means. We're not talking about a small discrepancy. We're not saying the void is 10% larger than models predict. We're saying it's 3 to 4 times larger than should be physically possible given the time available. That's not an error margin. That's a crisis in cosmology. Some researchers propose that the void started forming earlier than expected. Maybe tiny quantum fluctuations in the first moments after the Big Bang were larger in this region, giving matter a head start in moving apart. But quantum fluctuations are random by definition. For one to be large enough to create the Bootes void, it would need to be millions of times stronger than typical fluctuations. That's not random. That's an anomaly. Others suggested that dark energy played a role. Dark energy pushes space apart, accelerating the universe's expansion. If dark energy acted more strongly in the void's region, it could have pushed matter away faster than gravity pulled it together. But dark energy became dominant only about 6 billion years ago, roughly halfway through the universe's lifetime. Before that, gravity dominated. Dark energy can't explain why the void started forming so early. The merger theory offers a partial solution. If multiple smaller voids combined, The resulting structure could be larger than any single void formed independently. But even this explanation has problems. The smaller voids would each need to be enormous themselves, far larger than standard models predict, and they would need to merge in a way that creates perfect spherical symmetry. Here's the uncomfortable truth. Every attempt to explain the void using known physics requires either extraordinary coincidences or missing pieces in our understanding. Maybe gravity works differently on these scales. Maybe dark energy isn't uniform. Maybe the early universe had properties we haven't discovered yet. All of those maybes suggest the same thing. Something is wrong with our models. Or something else created the void. Something fast. Something powerful. Something that doesn't operate on geological timescales of billions of years, but on cosmological timescales of millions or less. When astronomers first published their findings, some colleagues suggested the void might be older than the universe itself, a remnant from before the Big Bang. That idea was quickly dismissed because nothing survives the Big Bang. The universe essentially resets at that moment, but the dismissal came from theoretical arguments, not evidence. We have no complete theory of what happened in the first fraction of a second after the Big Bang. Quantum effects dominated. Space and time themselves were still forming. The laws of physics, as we understand them, didn't fully apply. Could something have happened in that primordial chaos that seeded the void's formation? Something that gave it a massive head start? The time problem refuses to go away. Scientists can't wave it aside or explain it with small adjustments to existing theories. The void is there. It's real. And according to everything we know about how the universe evolves, it shouldn't be. Which means we need to know less than we think. 60 galaxies hang suspended through the void's center. They aren't scattered randomly throughout the empty sphere. They're arranged in a tube, a cylindrical structure cutting through 330 million light-years of nothing. This formation tells a story, but scientists argue about what that story means. When astronomers first found 8 galaxies in the void, they assumed those were random stragglers, galaxies that happened to be there when the void formed and simply never escaped. As surveys improved and the count climbed to 60, a pattern emerged. These galaxies aren't distributed spherically. They form a filament, thinner and less dense than normal filaments, but still organized. The tube runs through the void's center at a slight angle. Picture a straw pushed through a beach ball. The galaxies mark the straw's length, spaced millions of light-years apart, but aligned more precisely than random distribution would create. That alignment demands an explanation. The most popular theory says the tube marks where 2 smaller voids merged. When bubbles combine, they share a contact surface at first, a 2-dimensional membrane separating them. Galaxies near that membrane get caught between the expanding voids, trapped in the boundary region. As the membrane dissolves and the voids become one, those trapped galaxies remain, marking where the boundary used to be. This theory explains the cylindrical shape. The contact surface between 2 spherical voids would be circular, and galaxies caught along that circle would form a tube as the voids stretched along their merger axis. It's elegant. It matches other examples of void mergers in the universe, but it has problems. If the tube represents a merger boundary, it should contain more than 60 galaxies. Merger zones are crowded places where matter accumulates before getting pushed aside. The tube isn't crowded. It's nearly as empty as the rest of the void. Those 60 galaxies are spread so thin that calling it a structure almost feels generous. Also, the tube appears stable. The galaxies aren't flying apart or falling toward the void's edges. They're suspended, as if held in place by forces that balance perfectly. In a merger scenario, galaxies should still be moving, still responding to the gravitational chaos of 2 voids colliding. The tube suggests equilibrium, which suggests age, which brings us back to the time problem. Some of these galaxies are spiral galaxies, beautiful, pristine structures with well-defined arms and bright cores. Spiral galaxies are fragile. Gravitational interactions disrupt them easily. A close encounter with another galaxy can warp their arms or tear them apart entirely. Yet here they float in isolation, undisturbed, looking like they formed yesterday, even though they're billions of years old. Scientists call these void galaxies, field galaxies, orphans drifting between the major structures of the universe. Theory predicts they should be common in voids, the last holdouts from when matter tried to gather in these regions and failed. But 60 galaxies in this much space isn't common. It's extraordinary emptiness, even for a void. The void galaxies offer a unique opportunity for study. Galaxies in dense regions interact constantly. They merge, collide, pull on each other gravitationally. Those interactions drive evolution. They trigger star formation, feed black holes, and reshape galactic structure. The void galaxies evolved in near-perfect isolation. They represent what galaxies look like when nothing disturbs them. Except they look normal. That's the puzzle. If isolation produces distinctive features, the void galaxies should display those features. Different star populations, unusual shapes, signs of stunted evolution. But they don't. They could be galaxies from any region of the universe, just profoundly lonely. One galaxy in particular captures attention. Markarian 845 shines as the brightest member of the void. It's visible even with moderate amateur telescopes, a tiny smudge of light that has traveled 700 million years to reach Earth. Astronomers study it intensely, searching for clues about how galaxies behave in extreme isolation. What they find raises more questions. Markarian 845 appears to be forming stars at a normal rate. It has active regions, bright cores, all the hallmarks of a healthy galaxy. It's not dying from loneliness. It's thriving, somehow, despite having no neighbors for tens of millions of light years in any direction. The tube might not be a merger remnant at all. It might be something else entirely. A failed filament, perhaps. A region where matter tried to form a cosmic web structure but couldn't gather enough mass to complete the process. The result? A ghost of a filament, barely visible, marking what could have been. Or maybe the tube is actively maintained by forces we don't understand. Forces that keep those 60 galaxies positioned precisely where they are, preventing them from falling into the void's depths or escaping to its edges. That thought keeps some researchers awake at night, because maintained structures require mechanisms. And we haven't found one. Take a bottle of soap solution, blow bubbles into the air, watch them float, collide, and merge. 2 bubbles touch, form a shared wall, then pop into a single larger bubble. It happens in seconds. Now imagine that process on a cosmic scale, playing out over billions of years with voids instead of bubbles. That's the soap bubble theory, and it's our best guess for how the Bootes void formed. Voids don't start large, they start small, just regions where matter is slightly less dense than average. Gravity pulls matter from these underdense regions toward denser regions nearby. As matter leaves, the region becomes even less dense, which makes it easier for more matter to leave. The process feeds itself. A small void grows larger. The universe contains thousands of these growing voids. Most stay relatively small, ranging from 10 to 100 million light-years across. They exist between the filaments of the cosmic web, like air pockets in foam. Occasionally, 2 voids expand until they touch. When they do, something interesting happens. The boundary between 2 voids contains matter, galaxies, gas, dark matter, all pulled toward the edges as the voids expanded. When the voids merge, that boundary matter gets caught in the middle. Some galaxies fall into one void or the other. Some escape to the surrounding filaments, and some get stranded, suspended between the 2 expanding regions. If the voids are roughly equal in size and merge head-on, the result is a larger void with a roughly cylindrical collection of galaxies running through it. Sound familiar? That's exactly what we see in the Bootes void. The tube of 60 galaxies marks where the merger happened, like a scar running through the emptiness. Computer simulations support this theory. When researchers model void formation and merger, they see structures form that resemble the Bootes void. Not perfectly, but close enough to be compelling. Multiple small voids, each 50 to 100 million light-years across, merge over billions of years. The result is a supervoid, orders of magnitude larger than any of the component voids. But here's where the theory breaks down. For the soap bubble model to create the Bootes void, you need perfect conditions. The smaller voids need to be unusually large to begin with. They need to merge at precise angles. The timing needs to be exactly right. And all of this needs to happen in a universe that isn't old enough for natural processes to create voids that large in the first place. It's like saying a tornado can assemble a car from spare parts. Sure, if the conditions are exactly perfect and the parts are exactly positioned and pure luck aligns everything properly, maybe it could happen. But it's wildly improbable. Finding one example of it in a universe filled with voids would be remarkable. Finding multiple would be impossible. The Bootes void isn't the only supervoid. Others exist. The KBC void, which our own galaxy sits inside, measures over 2 billion light-years across. It dwarfs the Bootes void. The cold spot, a mysterious temperature depression in the cosmic microwave background, might be caused by an even larger void. These structures exist, and they all challenge the soap bubble theory's ability to explain them. Some researchers have modified the theory. Maybe dark energy plays a role. Maybe it accelerates void merger by pushing space apart faster than models predict. Maybe quantum effects in the early universe created larger than normal seed voids that grew into these monsters. Maybe the distribution of dark matter isn't as uniform as we assume, leading to unexpected void growth in certain regions. All of those maybes are patches on a theory that doesn't quite work. They're ways of forcing observations to fit existing frameworks rather than developing new frameworks to match observations. That's not necessarily bad science, but it's a sign that something fundamental is missing. The soap bubble theory remains our leading explanation because it's the best we have. It uses known physics. It produces results that look somewhat like what we observe, and most importantly, it doesn't require us to invoke exotic phenomena or rewrite textbooks. But best guess and correct answer aren't the same thing. The void exists. The theory explains part of how it formed. The gap between those two facts is where the real mystery lives, and that gap is growing. 68% of the universe is made of something we don't understand. We call it dark energy because we're bad at naming things. It's not dark. It's not energy in the traditional sense. But it's everywhere, and it's pushing the universe apart faster and faster. The Bootes void might be our best laboratory for studying this invisible force. Einstein's equations predicted dark energy decades before we discovered it. He called it the cosmological constant, and he added it to his equations to keep the universe static. When observations later showed the universe was expanding, Einstein called it his biggest blunder. Turns out he was right the first time, just for the wrong reasons. Dark energy doesn't pull, it pushes. Unlike gravity, which brings objects together, dark energy drives them apart. The effect is subtle on small scales. Gravity easily overcomes dark energy's push within galaxies and even within galaxy clusters. But on cosmic scales, across hundreds of millions of light-years, dark energy dominates. It's the reason the universe's expansion is accelerating. Think of space itself as stretchable fabric. Dark energy doesn't push objects through space. It stretches the space between objects. The farther apart two objects are, the more space exists between them, the stronger dark energy's effect becomes. Over billions of years, this stretching adds up. Voids grow, filaments spread apart, the cosmic web expands. The Bootes void represents a region where this process went into overdrive. Standard theory says voids form when gravity pulls matter toward dense regions, leaving underdense regions behind. Those underdense regions expand as the universe expands, creating voids. But the Bootes void expanded too fast, too completely. something accelerated the process beyond normal rates. One hypothesis says dark energy isn't uniform. Maybe it's stronger in some regions, weaker in others. In the void's location, dark energy could have been concentrated or more active, pushing matter away more aggressively than elsewhere. Over time, this created an enormous empty region, while surrounding areas developed normally. This hypothesis has problems. All our observations suggest dark energy is perfectly uniform throughout the observable universe. We measure its effects in dozens of different ways, from distant supernovae to the cosmic microwave background. Everything indicates dark energy has the same strength everywhere. Proposing it varies by location means proposing our observations are missing something huge. Another idea suggests dark energy interacts with dark matter in unexpected ways. Dark matter makes up about 27% of the universe. It provides the gravitational scaffolding around which normal matter gathers. If dark energy somehow affects dark matter's distribution, it could create regions where dark matter concentrations differ from predictions. The Bootes void could be a place where dark matter was pushed out early, preventing normal matter from gathering. Both ideas require physics beyond our current understanding. We don't have a complete theory of dark energy. We know it exists. We can measure its effects, but we don't know what it is, how it works, or why it has the strength it does. Adding new properties to an already mysterious phenomenon feels like guessing, yet the void demands explanation. Measuring its size, shape, and growth rate offers clues about dark energy's behavior. If the void is growing faster than the universal expansion rate, that tells us dark energy is stronger there. If it's growing at the same rate, that tells us dark energy is uniform and something else created the void's initial size. Astronomers have been tracking the void's boundaries for decades. Galaxies at the edge are moving away from the void's center, pushed by expanding space. By measuring their velocities and comparing them to the universal expansion rate, scientists can calculate how much dark energy is present. So far, results suggest the void is expanding at normal rates. That pushes against the concentrated dark energy hypothesis. But here's what keeps researchers interested. Voids provide the cleanest environment for studying dark energy's effects. In dense regions, gravity complicates everything. Multiple forces interact. Dark energy's push gets drowned out by gravitational attraction. In voids, dark energy is the only game in town. Matter is so sparse that gravity barely matters. If you want to see dark energy's fingerprints clearly, you study voids. The Bootes void, being the largest accessible supervoid, offers the best laboratory. Scientists can study how galaxies move near its edges, how the void's size changes over time, how structure formation differs inside versus outside. Each measurement constrains our models of dark energy and tells us whether our theories match reality. Missions like the Euclid satellite are designed specifically to study voids. By mapping thousands of voids across the universe and measuring their properties, astronomers hope to determine dark energy's equation of state. That's a fancy way of saying they want to know whether dark energy's strength changes over time or remains constant. The answer will reshape cosmology. If dark energy is constant, the universe will expand forever, growing colder and more empty until even atoms decay. If it's changing, the universe's fate could be dramatically different. It might reverse and collapse. It might tear itself apart. Understanding dark energy means understanding our cosmic future, and the Bootes void holds part of that answer. Emptiness has levels. The air you breathe contains trillions of molecules per cubic inch. The best laboratory vacuum on Earth reduces that to billions. The emptiness between Earth and the Moon drops it to millions. The space between stars contains maybe a few dozen particles per cubic inch. The Bootes void takes emptiness to an extreme that borders on philosophical. In normal regions of the universe, you encounter a galaxy every few million light years. Space isn't empty so much as sparse. Matter exists, just spread incredibly thin. Even between galaxies, intergalactic gas fills the void. Hydrogen atoms drift through space, one every few cubic inches. It's practically nothing by Earth standards, but it's something. The Bootes void is different, across its diameter, and you might encounter 60 galaxies across 330 million light-years. That works out to roughly one galaxy every 5 million light-years. Between those galaxies sits almost nothing. The intergalactic gas that fills normal space appears depleted here. Particles that should exist in background concentrations seem absent. This creates the most perfect vacuum known to science. More empty than any void we could create in a laboratory. More empty than the deepest intergalactic space in normal regions. So empty that matter and energy crossing through it experience almost zero interaction with anything else. When a photon enters the void from one edge, it travels 330 million light-years to the opposite edge without hitting a single atom. It doesn't scatter. It doesn't get absorbed. It doesn't interact with magnetic fields because there aren't enough charged particles to generate fields. It passes through unchanged, as if the void doesn't exist. The same happens with neutrinos. These ghostly particles barely interact with matter under normal circumstances. Trillions pass through your body every second without touching a single atom. In the void, neutrinos stream across hundreds of millions of light-years in perfect preservation. A pattern of neutrinos entering one side emerges on the other side identical, like a message traveling through time without degradation. This property makes the void a natural time capsule. Information encoded in particles could cross the void completely unchanged. In normal space, particles interact with gas, dust, magnetic fields. Those interactions scramble information, adding noise and distortion. The void preserves information perfectly across cosmic distances and cosmic timescales. Imagine sending a signal into the void today. That signal would take 330 million years to cross to the other side. When it emerged, it would be identical to when it entered, minus only the dimming from spreading across distance. Nothing along the way would have altered it. It would be a message from 330 million years in the past, perfectly preserved. The void's emptiness raises a question about particles with mass. Photons and neutrinos travel at or near light speed. They cross the void too quickly for gravity to affect them meaningfully. But slower particles would feel the void's gravitational structure, weak as it is. Those particles would gradually drift toward the void's edges over millions of years, pulled by the gravitational attraction of surrounding superclusters. This suggests the void acts like a sorting mechanism. Fast particles pass through, slow particles get filtered out. Over billions of years, the void becomes populated only by particles moving at enormous speeds, creating a unique environment unlike anywhere else in the universe. Scientists have proposed using the void to study fundamental physics. The lack of interaction means experiments could run for millions of years without interference. Want to test whether particles decay over extreme timescales? Send them through the void and detect them on the other side. Want to measure the universe's expansion with perfect accuracy? Use the void as a ruler. Knowing nothing inside it complicates the measurement. The void could also reveal whether empty space is truly empty. Quantum mechanics says even perfect vacuum contains virtual particles that pop in and out of existence. These quantum fluctuations should be detectable, but only if you can isolate a region from all other influences. The Bootes void might provide that isolation naturally. Standing inside the void would be an experience unlike anything possible in normal space. Look up and you see nothing. No stars except those in your local galaxy. No nebulae, no cosmic dust glowing in infrared. Just pure, unbroken darkness, stretching in every direction. The universe would feel not just empty but erased, as if someone deleted reality and left only a void. That darkness would be absolute. On Earth, light pollution washes out the night sky. In orbit around a planet in normal space, distant galaxies provide background illumination. In the void, no such light exists. Your eyes could adapt for hours and see nothing new because there's nothing to see. The void represents nature's closest approach to true nothingness. Not the mathematical concept of zero, but physical emptiness pushed to its extreme. And that extreme is teaching us what absence really means. Send a beam of light into the Bhute's void, and something remarkable happens. Nothing. Absolutely nothing. That beam travels for 330 million years, crosses 330 million light years, and emerges on the other side exactly as it entered. No scattering, no absorption, no change. This property transforms the void into something extraordinary. In normal space, particles interact constantly. Photons hit gas molecules and scatter. They encounter dust, grains, and get absorbed. Magnetic fields bend their paths. Even the supposedly empty space between galaxies contains enough matter to affect particle trajectories over cosmic distances. Information degrades. Signals blur. The universe acts like a noisy channel, adding static to every transmission. The void strips away that noise. Its extreme emptiness means particles experience almost zero interaction. A pattern of photons entering the void maintains its pattern across hundreds of millions of light years. This makes the void the perfect transmission medium, a cosmic fiber optic cable where information travels unchanged across unimaginable distances. Think about what that means for preservation. Information encoded today could survive hundreds of millions of years inside the void. Not just survive, but remain readable, recoverable, identical to when it entered. The void becomes a library where nothing decays because nothing exists to cause decay. Scientists have proposed using this property to study fundamental physics. Send a carefully constructed particle beam into the void. Wait 330 million years. Detect what emerges on the other side. Any changes in the beam would reveal physics we don't yet understand. Particle decay rates could be measured with perfect precision. The stability of fundamental particles could be tested over cosmological timescales. The catch is obvious. 330 million years. No human experiment can last that long. No civilization is guaranteed to survive that long. By the time results emerged, whoever sent the beam would be long gone. But the void doesn't care about human timescales. It operates on cosmic timescales where millions of years mean nothing. Natural particle beams already cross the void. Cosmic rays generated in one supercluster pass through and reach the other side. Neutrinos from supernovae stream across unimpeded. These natural experiments have been running for billions of years. If we could detect and analyze particles that cross the void, we could learn about events that happened hundreds of millions of years ago, preserved perfectly in particle streams. The void also affects particles with mass. Photons and neutrinos travel at or near light speed, crossing too quickly for gravitational effects to matter. But slower particles feel the void's gravitational structure. They experience a pull toward the edges, where superclusters provide weak but steady gravitational attraction. Over millions of years, this creates a sorting effect. Massive particles get pulled toward the boundaries and eventually leave the void. Light particles, moving too fast to be caught, pass through freely. The void becomes populated only by particles moving at extreme velocities, a high-speed highway where nothing slow survives. This has implications for dark matter. If dark matter particles move slowly, they should be pulled out of the void over time. If they move quickly, they should pass through unchanged. By measuring how much dark matter exists in the void compared to surrounding regions, scientists can constrain dark matter's velocity and interaction properties. The void becomes a dark matter detector, filtering particles based on their characteristics. Neutrinos present a special case. These particles rarely interact with anything under normal circumstances. They pass through entire planets without noticing. In the void, neutrinos experience perfect freedom. No obstacles, no fields, no interference. They travel in perfectly straight lines from source to detector, making the void ideal for neutrino astronomy. The Euclid satellite mission plans to use this property. By studying neutrino streams crossing voids, scientists can measure neutrino masses with unprecedented precision. Neutrinos barely have any mass, but that tiny mass affects how they travel. In normal space, interactions complicate measurements. In the void, those complications vanish. Imagine standing at one edge of the void and pointing a laser toward the other edge. That laser beam would travel for 330 million years without deviation. No gravitational lensing from intervening galaxies. No scattering from dust clouds. Just a perfectly straight line across 1% of the observable universe. When it finally reached the other side, it would still be carrying whatever information you encoded in its pattern. You could send a message, a signal, a record of human existence. That message would travel through time, preserved in the void's perfect vacuum, waiting to be received by whoever or whatever exists on the other side, 330 million years from now. The void becomes a bridge between epochs, a connection between the universe as it is now and the universe as it will be hundreds of millions of years hence. Information sent through it transcends the limitations of matter and energy in normal space. But here's the unsettling thought. If particles can travel through the void unchanged, preserving information across cosmic timescales, then information might already be traveling through. Signals sent millions or billions of years ago by sources we can't identify. Messages crossing the void right now, invisible to us because we're not looking for them or don't know how to decode them. The void might not be empty. It might be filled with information, passing through endlessly, waiting for someone to notice. 700 million light years away, inside the Bootes void, a spiral galaxy spins alone. Its catalog designation is MCG plus 01-02-015, but astronomers call it the loneliest galaxy in the universe. Look at an image captured by the Hubble Space Telescope and you see why. The galaxy appears perfect. Elegant spiral arms curve outward from a bright central core. Stars populate its disk in familiar patterns. Dust lanes trace the arms in dark silhouettes. Everything about it looks normal, except for one fact. It's completely isolated. The nearest neighboring galaxy sits tens of millions of light years away, invisible to any observer standing on a planet orbiting one of this galaxy's stars. Imagine living there. You develop telescopes. You scan the heavens. You see your own galaxy's stars, maybe some satellite dwarf galaxies orbiting nearby, and then nothing. Pure darkness stretching in every direction. You would discover the universe is far more empty than we believe it to be, because your perspective would be shaped by profound isolation. This galaxy challenges our understanding of how galaxies form and evolve. Standard theory says galaxies grow through mergers. Small galaxies collide and combine into larger ones. Gravitational interactions trigger star formation. Gas gets funneled into central black holes. The history of every galaxy is written in its scars from countless encounters with neighbors. The loneliest galaxy has no scars, no distorted spiral arms from a recent merger, no tidal streams of stars being torn away by a close encounter, no satellite galaxies orbiting it after being captured by gravity. It appears to have formed in perfect isolation and remained isolated for billions of years. That shouldn't produce a normal-looking spiral galaxy, but it did. Scientists study this galaxy intensely because it represents what galactic evolution looks like without interference. Every other galaxy we observe sits in an environment crowded with neighbors. Those neighbors affect everything. The loneliest galaxy evolved in a bubble of emptiness. Whatever properties it displays are intrinsic to galaxies themselves, not products of environmental factors. The galaxy appears to be forming stars at normal rates. That's strange. Star formation depends on gas supply and triggering mechanisms. Collisions and interactions trigger star formation bursts. In isolation, star formation should slow to a trickle as available gas gets used up. Yet this galaxy continues forming stars as if it had neighbors providing fresh gas through interactions. Its spiral structure remains intact. Spiral arms are fragile. They wind up over time, eventually smoothing out into featureless disks. Gravitational interactions can restart spiral waves, maintaining the pattern indefinitely. Without interactions, spiral structure should fade. The loneliest galaxy's crisp spiral arms suggest recent formation or unknown mechanisms maintaining structure in isolation. The central black hole appears active. Most galaxies contain supermassive black holes at their cores. These black holes grow by consuming gas and stars that fall into them. In dense environments, interactions provide steady fuel. In isolation, fuel sources should deplete. Yet something continues feeding this galaxy's central black hole. 59 other galaxies share the void with this one, but they're too distant to provide meaningful interaction. Space them out across 330 million light-years, and the distances between them range from millions to tens of millions of light-years. Gravitational effects become negligible at those separations. For all practical purposes, each void galaxy evolves alone. Some of these galaxies are elliptical, smooth, featureless blobs of stars. Others are irregulars, chaotic structures, lacking symmetry. But many are spirals, like the loneliest galaxy. Perfect, pristine, undisturbed. They float through the void like ships becalmed on an infinite ocean, moving but going nowhere. The void galaxies might represent the universe's most pristine examples of galactic evolution. They formed from the primordial gas left over after the Big Bang, without being polluted by material from previous generations of stars. They evolved in isolation, without being disrupted by neighbors. They offer a clean laboratory for studying how galaxies behave when left alone. But pristine doesn't mean simple. The loneliest galaxy raises as many questions as it answers. How did it form with such perfect structure? Why does it continue forming stars without external triggers? What maintains its spiral pattern without gravitational interactions to refresh the density waves? Standing on a planet in that galaxy, looking up at the night sky, you would see your home galaxies sweep across the heavens, billions of stars visible to the naked eye. Beyond that, nothing. The sky would end at your galaxy's edge. You could build the most powerful telescopes and see only darkness in all directions except one. In that one direction, incredibly faint and impossibly distant, you might detect a smudge of light, another galaxy, tens of millions of light-years away. You would understand intellectually that you're not alone in the universe, but you would feel alone, profoundly, existentially alone. The loneliest galaxy is us if we lived in hell. And somewhere in that galaxy, on a planet orbiting a star, maybe someone is looking back, wondering the same thing. Stand on a planet orbiting a star in one of the 60 void galaxies. Look up. This is what the universe shows you. Your home galaxy stretches across the sky, a river of stars from horizon to horizon. The familiar constellations, the dense core, the scattered outer arms, all visible in breathtaking detail. And beyond that, nothing. Not darkness like we know it, not night sky, scattered with distant stars, true emptiness. The kind of black that makes you question whether anything exists outside your galaxy at all. No Andromeda galaxy glowing softly, no Magellanic clouds hanging in the southern sky, no faint smudges marking galaxy clusters billions of light-years distant. Just black, absolute, complete. Your eyes would adapt the way they do under dark skies on Earth. Pupils would dilate. Rod cells in your retinas would reach maximum sensitivity. You would see fainter and fainter details in your own galaxy. But no amount of adaptation would reveal other galaxies because they're simply too far away. The nearest one sits tens of millions of light-years distant, far beyond the limit of naked eye visibility. Build a telescope, a small one at first, the kind early astronomers used to discover Jupiter's moons and Saturn's rings. Point it toward the darkness beyond your galaxy. You see nothing. Build a larger telescope, matching the great refractors of the 19th century. Still nothing. The darkness refuses to yield. Keep building. Use the largest mirrors, the most sensitive detectors. Eventually, with technology matching our best modern instruments, you might detect a faint smudge, a galaxy, incredibly distant, barely visible even with powerful equipment. That detection would be revolutionary. It would prove your galaxy isn't alone in the universe. But imagine the psychological impact. Humanity developed alongside a sky full of stars. We built mythologies around constellations. We navigated by stellar patterns. We drew inspiration from the vast canopy of lights above us. Growing up under a void sky would fundamentally reshape human psychology. Children wouldn't point at stars and ask about other worlds. They would grow up knowing the universe ends at their galaxy's edge. Philosophy would develop around isolation rather than connection. The question wouldn't be whether we're alone, but why we're alone. What did we do to deserve this cosmic exile? Religion would take darker forms. Maybe the void is punishment. Maybe it's protection. Maybe the universe once contained other galaxies, and they were all destroyed, leaving only yours as a survivor or a warning. The mythology possibilities are endless, and none of them are comforting. Science would advance differently. Without observing other galaxies, the concept of galactic evolution wouldn't develop. The idea that your galaxy is one of trillions would seem absurd. Cosmology would focus inward, studying your galaxy's structure rather than the universe's structure. The Big Bang might never be discovered because crucial evidence comes from distant galaxy observations. The cosmic microwave background would still be detectable. You would measure that ancient radiation and develop theories about the universe's beginning. But without seeing other galaxies, without measuring their distances and velocities, you wouldn't have the full picture. Your cosmology would be incomplete, built on partial evidence. Eventually, with advanced enough telescopes, you would detect more galaxies, not dozens or hundreds, but 60 across the entire observable sky. 60 points of faint light scattered randomly, separated by vast distances. That discovery would reshape everything. You would realize you're inside something, a bubble of emptiness, a cosmic void. The void's boundaries would be impossible to miss once you had the technology to detect them. In every direction, hundreds of millions of light years away, you would see walls of galaxies. Massive superclusters containing thousands of galaxies each, arranged in spherical shells around your position. You're at the center of a cosmic bubble, and the universe you believed was mostly empty is actually mostly full. That revelation would be terrifying. Your entire history took place inside an anomaly. Your isolation wasn't random. The void's structure, its perfect spherical symmetry, the way the walls surround you at equal distances, all suggests something created this, or something is maintaining it. You're not just alone, you're contained. The day sky would look normal. Your star provides light, planets orbit, moons hang in familiar positions. Everything seems ordinary until sunset. Then the universe reminds you where you are. The darkness descends, the galaxy appears overhead, and the void presses in from all sides, vast and empty and waiting. Poets would write about the darkness, artists would paint it, philosophers would debate its meaning, and everyone, at some point in their lives, would stand outside at night and stare into the black space between stars, wondering what lies beyond, wondering if they'll ever escape. We live in a universe filled with galaxies. They see a universe that's almost empty. Both perspectives are correct, and somewhere between those perspectives lies the truth about what the void really is. 5 massive structures encircle the Bootes void like cosmic prison walls. The Ursa Major supercluster, the Shapley supercluster, the Hercules supercluster, the Corona Borealis supercluster, and the Bootes supercluster itself. Each contains thousands of galaxies bound together by gravity. Each sits at the void's boundary, defining its edge with almost geometric precision. This arrangement isn't random, The 5 superclusters form a rough sphere around the void's emptiness, positioned at roughly equal distances from its center. If you mapped their locations in 3 dimensions, you would see vertices of a polyhedron, a geometric solid enclosing empty space. That pattern demands explanation. The Ursa Major supercluster sprawls across the northern sky as seen from Earth. It contains hundreds of galaxy groups, each containing dozens of galaxies. Gravity holds the structure together despite the universe's expansion trying to pull it apart. The supercluster sits at one edge of the void, marking where emptiness meets matter. The Shapley supercluster lies in the opposite direction, one of the most massive structures in the local universe. It contains over 8,000 galaxies arranged in multiple clusters and groups. Its gravitational pull affects regions hundreds of millions of light-years away, and it defines the void's far boundary, a wall of matter where the emptiness ends. The other 3 superclusters complete the enclosure, each massive in its own right, each containing more galaxies than the entire void holds. Together, they form a shell around emptiness, as if the void exists in the space between them rather than they existing around the void. This raises a question cosmologists argue about. Did the superclusters create the void by pulling matter toward themselves, leaving a depleted region in the middle? Or did the void form first, and matter accumulated at its boundaries, creating the superclusters? Cause and effect become unclear when the structures are this large and this old. Standard theory suggests the former. Superclusters form from overdense regions in the early universe. Gravity pulls matter toward these regions over billions of years. The space between superclusters gets depleted as matter migrates toward denser areas. This creates voids naturally as a byproduct of structure formation. But the Bootes void's symmetry challenges this explanation. If 5 superclusters randomly pulled matter toward themselves, the resulting void should be irregular. It should show signs of asymmetric depletion, with matter pulled more strongly toward the most massive superclusters. Instead, the void is nearly spherical, suggesting balanced forces acting equally in all directions. An alternative theory proposes the void formed from a localized underdense region in the early universe. Quantum fluctuations created a bubble where matter density was lower than average. As the universe expanded, this bubble expanded with it. Matter at the bubble's edges, caught between the expanding void and neighboring dense regions, got compressed into the structures that became superclusters. This model explains the symmetry. A spherical, underdense region creates a spherical void. Matter accumulates symmetrically at the boundaries. The superclusters form where void meets non-void, marking the transition from emptiness to structure. It's elegant and matches observations reasonably well, except for the time problem. Creating a void this large from initial underdensity requires that underdensity to be enormous. Quantum fluctuations don't create differences that large. You would need something extraordinary in the early universe, something beyond normal physics, to seed a structure this massive. The walls themselves provide clues. Scientists study galaxies at the void's boundary, measuring their velocities and distributions. These galaxies show peculiar motions, moving faster than the universal expansion rate would suggest. Something appears to be pulling them away from the void, or pushing them toward the superclusters. That something is gravity, but the calculations don't quite work. The observed velocities require more mass in the superclusters than we can detect. Dark matter provides some of the missing mass, but even including dark matter, the numbers fall short. Either we're missing mass we haven't detected yet, or our understanding of gravity on these scales is incomplete. The walls aren't perfectly solid. Filaments of galaxies connect the superclusters, stretching across the void's boundaries like bridges. These filaments carry matter from one supercluster to another, maintaining connections in the cosmic web. But the filaments avoid the void's interior. They curve around it, as if repelled by the emptiness. That avoidance suggests the void isn't just an absence of matter, it's an active structure that influences its surroundings. Matter doesn't simply leave the void through random motion, it gets pushed out or prevented from entering in the first place. The walls aren't just boundaries, they're barriers, maintained by processes we don't fully understand. 5 superclusters, 5 points defining a sphere, 5 walls enclosing darkness. The geometry is too perfect to be coincidence. Yet cosmology doesn't provide mechanisms for creating perfect geometric structures. Nature creates chaos, complexity, fractals. It doesn't create polyhedrons, unless something other than nature created the void, unless the walls aren't natural formations but constructed boundaries, unless we're looking at the largest engineered structure in the observable universe. That thought keeps some researchers awake, because walls serve a purpose. They contain or exclude, and the Boute's void is definitely contained. 60 galaxies drift through the void. They're not just any galaxies, they're strange, different. Scientists call them void galaxies or field galaxies, and they represent something cosmology never predicted. These galaxies shouldn't look the way they do, they shouldn't behave the way they do, yet there they float, defying expectations. Standard galaxy formation theory depends on interactions. Galaxies form when gas clouds collapse under gravity. They grow by merging with smaller galaxies. They evolve through encounters with neighbors. Tidal forces from nearby galaxies trigger star formation. Collisions reshape structures. Every galaxy's history is written in features created by billions of years of gravitational chaos. Void galaxies evolved without chaos. They formed in isolation, grew in isolation, and spent billions of years without meaningful interactions with neighbors. Theory predicts this should produce distinctive features: different star populations, unusual chemical compositions, stunted evolution. The void galaxies should look primitive, underdeveloped, strange. They look completely normal. That's the mystery. Take spectra of void galaxies, and you find elements in expected proportions: carbon, oxygen, iron, all present at concentrations matching galaxies in dense regions. This means void galaxies underwent normal stellar evolution. Stars formed, lived, exploded as supernovae, and enriched surrounding gas with heavy elements, all without the interactions that supposedly drive these processes. Measure their star formation rates, and you find them forming stars at normal or even elevated rates. This contradicts models that say interactions trigger star bursts. Void galaxies, lacking neighbors to interact with, should have exhausted their gas supplies billions of years ago. Instead, they're actively making new stars, pulling gas from somewhere to fuel continued formation. Look at their morphologies and you see spirals, ellipticals, and irregulars in roughly the same proportions as the general galaxy population. Spiral galaxies maintain tight, well-defined arms. Elliptical galaxies show smooth, regular shapes. Nothing about their appearances suggests evolution in extreme isolation. They could be galaxies from anywhere in the universe, just profoundly lonely. Some researchers propose void galaxies are recent arrivals. Maybe they formed elsewhere and migrated into the void through peculiar velocities or gravitational perturbations. That would explain why they look normal. They spent most of their lives in typical environments and only recently entered isolation. The problem with this theory is velocity. Galaxies don't move fast enough to cross tens of millions of light years in less than 1 billion years. Any galaxy that entered the void recently would show signs of recent passage, distorted structures, trailing streams of gas, evidence of the violent environment it left behind. The void galaxies show none of this. Another hypothesis suggests void galaxies formed from pristine gas, material that never participated in earlier generations of star formation. This primordial gas would have unique properties, potentially allowing more efficient star formation than recycled gas. The void galaxies would be younger than they appear, formed relatively recently from leftover Big Bang material, Spectroscopic studies contradict this. Void galaxies contain heavy elements that can only form inside stars. Multiple generations of stars must have lived and died to produce the observed chemical compositions. These aren't young galaxies formed from primordial gas. They're old galaxies with complex stellar histories. The void galaxies might represent the purest test of galaxy evolution theory. Strip away environmental effects, and you isolate intrinsic galactic properties. Whatever processes drive star formation, maintain spiral structure, and regulate galactic evolution must be internal to galaxies themselves, independent of interactions. This has profound implications. If galaxies can evolve normally in complete isolation, then interactions aren't essential to galactic life cycles. They might accelerate certain processes or trigger specific events, but they're not fundamental requirements. Galaxies are more self-sufficient than models assumed. But here's what troubles astronomers. Some void galaxies show features that shouldn't exist without interactions. Spiral arms, for instance, wind up over hundreds of millions of years unless something refreshes them. In dense regions, nearby galaxies provide gravitational perturbations that maintain spiral patterns. In isolation, spirals should fade. The void galaxies have crisp, well-defined spiral arms. Something maintains them. Either these galaxies are much younger than their stellar populations suggest, or unknown mechanisms preserve spiral structure without external influences. Neither explanation fits comfortably with existing theory. A few void galaxies show signs of recent star formation bursts. Their spectra reveal young, hot stars formed within the last few million years. In dense regions, such bursts follow collisions or close encounters. In the void, no collision partners exist. What triggered the bursts? Maybe void galaxies aren't as isolated as they appear. Maybe dark matter halos extend farther than visible matter. Maybe void galaxies pass through each other's dark matter halos, experiencing gravitational interactions we can't directly observe. That could provide the missing mechanism for maintaining structure and triggering star formation. Or maybe something else lives in the void, something we haven't detected yet, something that interacts with galaxies and drives their evolution in ways we don't understand. The void galaxies aren't isolated at all. They're just isolated from us. The Bootes Void is a laboratory, the largest, cleanest, most perfect laboratory for studying fundamental cosmology that nature provides. Scientists have spent decades pointing instruments at it, measuring everything they can because the void's extreme properties make it ideal for testing theories that are impossible to test anywhere else. Dark matter mapping begins with the void. Dark matter doesn't emit light. We can't see it directly, but we can map its distribution by observing how it affects visible matter through gravity. In dense regions, this gets complicated. Multiple gravitational sources overlap. Galaxies, clusters, filaments all contribute. Separating individual contributions becomes nearly impossible. The void simplifies everything. With so few galaxies present, gravitational effects come from dark matter almost exclusively. Any anomalous motions, any unexpected velocities, trace directly to dark matter's distribution. By tracking how the 60 void galaxies move, scientists can map dark matter throughout the entire void volume. Results have been surprising. Dark matter doesn't avoid the void completely, as some theories predicted. It's present, just distributed differently than in dense regions. Instead of concentrated clumps, dark matter in the void forms thin, extended structures, like cobwebs stretched across emptiness, connecting the sparse galaxies and linking them to the surrounding superclusters. This distribution tells us about dark matter's properties. If dark matter interacted strongly with itself, it would clump more densely. If it moved at high velocities, it would spread more evenly. The observed distribution suggests dark matter is cold, meaning it moves slowly, and collisionless, meaning it doesn't interact with itself or normal matter except through gravity. Gravitational lensing provides another measurement tool. When light passes near massive objects, gravity bends its path. This bending creates distortions in background images, like looking through warped glass. By studying how light from distant galaxies gets distorted while passing through the void, scientists can measure the void's total mass. The measurements reveal the void contains about 10% of the matter density found in typical regions, not zero, but drastically reduced. That 10% includes both normal matter in the 60 galaxies and dark matter distributed throughout. The dark matter component outweighs visible matter by roughly 5 to 1, matching the universal average. This ratio is crucial. If the void had formed by something selectively removing normal matter while leaving dark matter behind, the ratio would differ from the cosmic average. Instead, the void appears depleted in both types of matter equally. Whatever created the void affected all matter, not just galaxies. The void also serves as a test bed for modified gravity theories. Some physicists propose that gravity behaves differently on cosmic scales than Einstein's equations predict. These modified gravity theories could explain cosmic acceleration without requiring dark energy. Testing these theories requires observations in regions where gravity is the dominant force. Voids provide perfect testing grounds. With minimal matter present, gravity's effects stand out clearly. If modified gravity theories are correct, galaxies in voids should move differently than Einstein's equations predict. Decades of observations show void galaxy motions match Einstein's predictions exactly. Modified gravity theories keep getting ruled out. Dark energy measurements rely heavily on void studies. Dark energy's strength determines how fast voids grow over time. By measuring void expansion rates and comparing them to predictions, scientists constrain dark energy's properties. The Bootes void, being large and well studied, provides the most precise measurements available. Current data suggests the void expands at a rate consistent with uniform dark energy throughout the universe. No evidence exists for dark energy concentration or variation. The void grows because the universe grows, driven by the same dark energy that pushes galaxies apart everywhere. That uniformity supports the simplest dark energy models and rules out many exotic alternatives. Neutrino studies use the void as a detection volume. Neutrinos stream through space, barely interacting with anything. In dense regions, the few interactions that do occur create background noise that obscures signals. In the void, background noise drops to nearly zero. Neutrinos crossing the void can be detected and studied with minimal interference. The Euclid satellite mission, launched to study cosmic structure, dedicates significant observation time to voids. By mapping thousands of voids across the universe and measuring their properties, Euclid will constrain dark energy's equation of state. This single number determines the universe's ultimate fate. The Bootes void contributes the largest single data point to that measurement. Cosmic microwave background studies connect to void research. The background radiation shows tiny temperature fluctuations corresponding to density variations in the early universe. Voids should leave imprints on this radiation, cold spots where light lost energy while crossing underdense regions. The cold spot, a mysterious temperature depression in the background, might be the imprint of a supervoid even larger than the Bootes void. Every measurement refines our understanding. Every observation tests another theory. The void has become one of the most studied regions in cosmology despite containing almost nothing. Or perhaps because it contains almost nothing. In science, sometimes the most important discoveries come from studying what isn't there. Trillions of neutrinos pass through your body right now. They come from the core of our star, where nuclear fusion reactions produce them by the billions per second. They travel at nearly light speed, cross 93 million miles in 8 minutes, and pass through Earth as if it doesn't exist. You never notice. They barely notice you. Neutrinos are ghosts. They have almost no mass and interact with matter so weakly that a light year of lead wouldn't stop them. Only one in many billions interacts with an atom as it passes through Earth. Detecting them requires massive instruments buried deep underground to shield from other particles filled with thousands of tons of ultra-pure water or other materials, waiting months or years to catch a single neutrino interaction. The Boötes void changes everything. It's the largest neutrino detector ever conceived, 330 million light-years of near-perfect emptiness, where neutrinos travel completely unimpeded. No interactions, no background noise, no interference, just pure signal crossing cosmic distances. Neutrinos come in three types, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They can transform from one flavor to another while traveling, a phenomenon called oscillation. The oscillation rate depends on their masses, and measuring those masses is one of cosmology's great challenges. Standard neutrino detectors on Earth measure oscillations over distances of hundreds or thousands of miles. Results give us information about mass differences between flavors, but not absolute masses. To measure absolute masses, you need longer baselines, bigger distances for oscillations to play out fully. The void provides baselines, measured in hundreds of millions of light-years. Neutrinos entering one edge emerge on the other side 330 million years later. Any oscillations have had time to complete countless cycles. By detecting neutrinos that cross the void and measuring their flavor composition, scientists can determine absolute neutrino masses with unprecedented precision. This measurement matters enormously. Neutrinos are the second most abundant particle in the universe after photons. Their mass, tiny as it is, contributes to the universe's total mass-energy budget. Knowing neutrino masses tells us how structure formed in the early universe, how galaxies clustered, how voids developed. It constrains dark energy models and tests particle physics theories. The void also reveals neutrino sources. Neutrinos come from many places. Stars produce them through fusion. Supernovae produce them in tremendous bursts. Active galactic nuclei produce them through particle acceleration near supermassive black holes. Each source has a characteristic energy spectrum, a signature that identifies where the neutrinos originated. In dense regions, neutrinos from different sources mix together. Separating signals becomes difficult. The void acts as a filter. Any neutrino detected while crossing the void must have originated from sources outside the void. This narrows down possible origins and makes identification easier. Supernova neutrinos are particularly interesting. When massive stars explode, they release 99% of their energy as neutrinos. These neutrinos escape seconds before the visible explosion, carrying information about the star's core collapse. If a supernova occurred in one of the superclusters surrounding the void, its neutrino burst would cross the void largely unchanged. Detecting such a burst would provide a pristine window into supernova physics. The neutrinos would arrive before the light, announcing the explosion. Their energies and flavors would reveal details about nuclear reactions in the collapsing core. And because they crossed the void without interaction, the data would be cleaner than any supernova neutrino signal detected from events in normal space. Cosmic neutrinos present another opportunity. The Big Bang produced a background of neutrinos, similar to the cosmic microwave background of photons. This cosmic neutrino background should exist throughout the universe, but it's never been detected directly. The neutrinos are too low energy to trigger reactions in current detectors. The void might make detection possible. With 330 million light-years of detection volume and almost zero background interference, even weak signals could accumulate to detectable levels. A future neutrino detector using the void as its volume could make the first direct observation of cosmic neutrinos, confirming a major Big Bang prediction. Dark matter might produce neutrinos. Some theories predict dark matter particles occasionally annihilate, producing normal particles including neutrinos. These annihilation events would be rare and spread throughout space, making them nearly impossible to detect in most regions. But the void's emptiness amplifies any excess neutrino flux. If dark matter produces neutrinos through annihilation, the void should show a specific neutrino signature. Researchers have searched for this signature without success so far, which constrains dark matter properties. Either dark matter doesn't annihilate, or it does so at rates too low for current instruments to detect. The Euclid satellite and next-generation neutrino telescopes plan coordinated observations. Euclid maps void structure and galaxy distributions. Neutrino telescopes detect particles crossing those voids. Together, they create three-dimensional maps showing how neutrinos flow through cosmic structure, revealing properties impossible to measure any other way. The void isn't just empty space. It's an instrument. Nature built a particle detector 330 million light-years across and pointed it at the universe. We just have to learn how to read what it's detecting. The universe is expanding. Galaxies move away from each other as space itself stretches. Edwin Hubble discovered this in 1929, fundamentally changing our understanding of reality. But the expansion isn't uniform, it's accelerating, driven by dark energy pushing space apart faster and faster. The Bootes void is growing, and the rate at which it grows tells us secrets about cosmic acceleration. Measure galaxies at the void's edge, track their velocities. They're moving away from the void's center, pushed by expanding space. The velocity increases with distance, exactly as Hubble's law predicts. But small deviations from perfect Hubble flow reveal the void's influence on surrounding space. Galaxies just outside the void move slightly faster than expected. The void acts like a bubble, pushing outward on its boundaries. This push comes from the interplay between gravity pulling matter together and dark energy pushing space apart. In the void, dark energy dominates because there's too little matter for gravity to counteract it effectively. Scientists can calculate the void's expansion rate from these velocity measurements. If dark energy is uniform throughout the universe, the void should expand at a specific rate determined by the universal dark energy density. Measure faster expansion and dark energy must be stronger in the void. Measure slower expansion and dark energy must be weaker. Decades of observations converge on a single answer. The void expands at exactly the rate predicted for uniform dark energy. No evidence exists for variation. No indication that dark energy concentrates or depletes in different regions. The void grows because the universe grows, nothing more. This uniformity is both reassuring and frustrating. Reassuring because it confirms our simplest dark energy models. Frustrating because it doesn't explain why the void is so large or how it formed. Uniform dark energy can explain the void's current growth, but not its initial creation. The expansion rate also reveals the void's age. By running the expansion backward in time, scientists can estimate when the void first formed. The math suggests the void began emerging roughly 10 to 12 billion years ago, within a few billion years of the Big Bang. That timing creates the time problem mentioned earlier. The void is almost as old as the universe itself. Compare the void's expansion to void expansion elsewhere in the universe. Smaller voids grow at different rates depending on their sizes and surrounding matter densities. Larger voids grow faster. More isolated voids grow faster. Voids near superclusters grow slower because gravitational attraction from surrounding matter partially counteracts dark energy's push. The Bootes void should grow relatively slowly. It's surrounded by 5 massive superclusters exerting substantial gravitational pull. That pull should slow expansion at the void's edges, preventing it from growing as fast as an isolated void would. Instead, the void expands as if those superclusters don't exist. This suggests the void is older or larger than the superclusters. It established its size before the superclusters formed, and now it's too large for their gravity to affect significantly. The superclusters formed at the void's edges, marking where matter accumulated after being pushed out by the void's expansion. Dark energy's equation of state comes from expansion measurements. This equation describes how dark energy's density changes as the universe expands. If the density remains constant, dark energy behaves like Einstein's cosmological constant. If it changes, dark energy is something more exotic, possibly evolving over time. Void expansion rates constrain this equation. The Bootes void, being large and nearby, provides particularly precise constraints. Combine its data with measurements from hundreds of other voids mapped by surveys like the Sloan Digital Sky Survey, and you get one of the most accurate determinations of dark energy's equation of state available. Current results indicate dark energy behaves like a cosmological constant to within a few % uncertainty. Its density remains constant as the universe expands. This rules out many exotic dark energy models and supports the simplest explanation. Dark energy is a property of space itself, a fundamental constant woven into reality's fabric. But a few % uncertainty leaves room for surprises. If future observations reveal the void expanding slightly faster or slower than predicted, it would revolutionize cosmology. It would mean dark energy is more complex than we thought, possibly evolving, possibly varying by location. The universe's fate would become uncertain again. Researchers monitor the void continuously, measuring expansion rates with increasing precision, comparing results from different voids, searching for deviations from predictions. Each new measurement either confirms existing models or hints at something new. The void is expanding. That much is certain. How fast it expands, and what that speed reveals about dark energy, remains one of cosmology's most important ongoing investigations. The answer will determine whether the universe expands forever, eventually tears itself apart, or does something we haven't imagined yet. And the Bootes void, by simply growing, helps us find that answer. Space has a temperature, not the kind you feel, because space is mostly empty and there's nothing to conduct heat. But the gas and dust floating through space, the photons streaming across cosmic distances, the energy permeating every region, all have measurable temperatures. And the Bootes void is cold. The cosmic microwave background provides a reference temperature. This ancient radiation fills the universe uniformly at about 2.7 degrees above absolute zero. It's the leftover heat from the Big Bang, cooled by 13.8 billion years of expansion. Every region of space sits bathed in this radiation, maintaining a baseline temperature. Voids are colder than this baseline. Photons crossing voids lose energy, climbing out of the void's gravitational potential well. This energy loss appears as temperature reduction, a phenomenon called the Sachs-Wolf effect. The larger and deeper the void, the more energy photons lose, the colder the void appears. The Bootes void shows this effect clearly. Measurements of microwave background radiation passing through the void reveal temperature drops of a few millionths of a degree. Tiny by everyday standards, but significant in cosmology. This temperature depression confirms the void's low density and provides independent verification of its size. Intergalactic gas adds to the temperature difference. In dense regions, gas gets heated by star formation, supernovae, and radiation from active galaxies. This hot gas emits X-rays detectable by space telescopes. The gas temperature reaches millions of degrees in galaxy clusters, creating glowing halos around massive structures. The void contains almost no hot gas. What little gas exists there remains cold, unheated by stellar processes, because stars are so rare. X-ray observations show the void as a dark region, devoid of the hot gas that marks galaxy-rich areas. This absence reinforces the void's emptiness and provides another measurement of how little matter it contains. Magnetic fields relate to temperature. In normal space, supernova explosions and active galaxies generate magnetic fields that thread through intergalactic gas. These fields store energy and can heat surrounding material through reconnection events. The void's magnetic fields should be much weaker, unable to contribute significant heating. Measurements confirm this. Polarization, studies of radio waves crossing the void, show minimal magnetic field strength. What fields exist appear to be remnants from earlier epochs, stretched thin by cosmic expansion. They're too weak to affect gas temperature or influence particle motion meaningfully. The temperature difference has practical implications. Cold regions allow better observation of certain phenomena. The cosmic microwave background variations, for instance, show up more clearly against the void's cold backdrop. Researchers studying the background's finest details preferentially observe sightlines passing through voids to maximize signal clarity. Neutrinos care about temperature. Higher temperatures mean more particle interactions, more background noise, more difficulty detecting rare events. The void's coldness reduces this noise, making it an ideal environment for neutrino astronomy. Particles crossing the void encounter minimal thermal radiation that could interfere with measurements. The cold spot presents an extreme case. This mysterious region in the cosmic microwave background appears significantly colder than any standard void should produce. Discovered in 2003, it spans roughly 5 degrees on the sky and shows a temperature depression about 70 millionths of a degree below average. Some scientists propose the cold spot marks a supervoid larger than the Bootes void. Initial surveys found evidence for such a void along the cold spot's line of sight, but subsequent observations raised doubts. The supervoid might not be large enough to explain the full temperature depression. Alternative theories invoke exotic physics, statistical flukes, or even collisions with parallel universes. The Bootes void's temperature properties help constrain cold spot theories. By measuring how much temperature depression the Bootes void creates and comparing it to the cold spot, researchers can estimate what size void would be needed to explain the observation. Current analysis suggests something unusual is happening with the cold spot beyond simple void effects. Temperature gradients appear at void boundaries. Where void edges meet superclusters, gas temperature rises sharply. The transition from cold emptiness to hot dense regions happens over relatively short distances, creating cosmic weather fronts. These fronts might influence galaxy formation and evolution at void edges in ways not yet fully understood. Dark matter might affect temperature distributions. Though dark matter doesn't interact electromagnetically and can't be heated directly, its gravitational influence affects how normal matter distributes and heats. The void's dark matter distribution could create temperature patterns that reveal dark matter's properties. Studying these patterns requires extremely sensitive instruments. The temperature differences are tiny, separating genuine signals from instrumental noise and foreground contamination challenges even the best observatories. But as technology improves, temperature mapping becomes more precise, revealing subtle details about cosmic structure. The void is colder than its surroundings. That coldness is a signature, a fingerprint of extreme underdensity written in microwave photons and intergalactic gas. It's one more piece of evidence confirming the void's extraordinary nature and one more tool for probing the physics of cosmic expansion. When standard physics can't explain something, scientists explore alternatives. The Bootes void has spawned dozens of exotic theories, each trying to solve the mysteries that conventional cosmology struggles with. Some are speculative but plausible. Others drift into science fiction territory. All of them reveal how desperate we are for answers. Quantum fluctuation theory proposes the void originated from an exceptionally large random fluctuation in the early universe. Quantum mechanics allows brief violations of conservation laws through uncertainty principles. In the universe's first moments, when everything was quantum scale, enormous fluctuations might have occurred that are impossible now. One such fluctuation could have created a bubble of lower energy density. As the universe expanded, this bubble expanded with it, growing into the Bootes void. The 60 galaxies formed from matter caught at the bubble's edges, marking the transition zone between normal density and void. The problem is probability. Quantum fluctuations follow statistical distributions. Small fluctuations are common, large ones are rare. Fluctuations large enough to create the Bootes void are so improbable they should never occur in a universe our size and age. Finding one suggests either extraordinary luck or something wrong with our understanding of early universe quantum mechanics. Modified dark energy theories propose that dark energy isn't uniform. Perhaps it comes in domains, regions where its strength varies. The void sits in a strong dark energy domain. More aggressive cosmic acceleration in this region pushed matter away faster than elsewhere, creating exceptional emptiness. This requires dark energy to have properties we've never observed. All measurements suggest dark energy is uniform to extraordinary precision. Proposing variations demands explaining why we don't see those variations everywhere, and why they would concentrate in a single massive domain rather than appearing in many smaller regions. Primordial black hole theories suggest the void contains a massive black hole at its center. Not a stellar mass black hole, but something far larger, millions or billions of times our star's mass. This black hole formed in the early universe and spent billions of years consuming surrounding matter, creating the void as it fed. The theory fails observationally. Black holes that massive should be detectable through gravitational lensing, X-ray emission from infalling gas, and perturbations in nearby galaxy motions. No evidence exists for such an object. The void center appears empty by every measure. Repulsive dark matter theories propose that dark matter comes in two types, attractive and repulsive. Most dark matter attracts normally through gravity, but a small fraction repels ordinary matter. A concentration of repulsive dark matter in the void region pushed normal matter away, creating the observed structure. This requires inventing entirely new particle physics. No evidence supports repulsive dark matter. No theory predicts it. The idea exists purely to explain the void, which makes it scientifically unsatisfying. Good theories explain multiple phenomena. Theories invented to explain single observations rarely pan out. Cosmic string theories involve defects in space-time formed during the universe's earliest moments. These strings are thin, incredibly dense filaments stretching across cosmic distances. A network of cosmic strings could shape matter distribution, creating voids where strings repel matter and dense regions where they attract it. Cosmic strings likely exist based on particle physics theory, but we've never detected them. Searches using gravitational lensing, gravitational waves, and cosmic microwave background observations have found no evidence. If strings exist, they're too weak or too rare to explain major structures like the Booty's void. Domain wall theories propose that the void marks a boundary between different vacuum states of reality. Particle physics predicts the vacuum can exist in multiple stable states. Transitions between states create domain walls, two-dimensional surfaces where physics differs slightly on either side. A spherical domain wall could enclose the void, preventing matter inside from behaving like matter outside. Galaxies can't form normally inside the wall, explaining the void's emptiness. The 60 galaxies formed right at the wall, in the transition zone. Domain walls would be detectable through their gravitational effects and their impact on passing light. No observations support their existence. Like many exotic theories, domain walls are possible in principle, but lack observational backing. False vacuum decay theories suggest the void represents a region where the vacuum transitioned to a lower energy state. This transition created a bubble that expanded at light speed, clearing out matter as it went. The bubble eventually stopped growing, leaving a vast, empty region. False vacuum decay should produce specific signatures: temperature anomalies, particle production, remnant radiation. None appear in the void. If decay occurred, it happened in ways that left no traces we can detect, which seems unlikely given the process's violence. Multiverse collision theories propose the void marks where our universe collided with another universe in the larger multiverse. The collision disrupted matter distribution, creating a massive void along the impact site. The surrounding superclusters formed from matter compressed by the collision's shockwave. This theory is unfalsifiable with current technology. We can't observe other universes or detect collision evidence definitively. The void structure might match collision predictions, but it also matches many other predictions. Without unique signatures, the theory remains pure speculation. Every alternative theory shares a weakness. They require new physics or extremely unlikely events. Standard cosmology might struggle with the void, but at least it uses known physics. Alternative theories multiply mysteries rather than solving them. Yet, the void exists, observationally confirmed, undeniably strange. Standard theory can't explain it satisfactorily. Alternative theories feel like desperate grasping. Somewhere between those extremes lies the truth. We just haven't found it yet. Here's where science meets science fiction. Here's where serious astronomers whisper theories they wouldn't dare publish. Here's where the Bhutas void becomes less a mystery and more a horror story. What if the void isn't natural? What if something made it? Freeman Dyson proposed in 1960 that advanced civilizations would eventually enclose their stars in spheres to capture all energy output. These Dyson spheres would be impossible to miss. Stars would vanish from visible light observations, replaced by infrared sources as the spheres radiated waste heat. Now scale that up. Imagine a civilization millions or billions of years old, technology so advanced it makes ours look like stone tools, resources accumulated across countless millennia. Such a civilization wouldn't stop at enclosing one star. It would enclose thousands, millions, eventually, entire galaxies. A galaxy enclosed in Dyson spheres would disappear from our view. No visible light escaping, just infrared radiation from the sphere's outer surfaces. From our perspective, the galaxy would simply cease to exist. It would become invisible, removed from observable reality while still occupying space. Now imagine this civilization expanded outward from its home galaxy. It encountered neighboring galaxies and enclosed them too. The process snowballed. Each enclosed galaxy provided more energy, more resources, more capability to enclose additional galaxies. The civilization spread like a wave across the universe. 700 million years ago, roughly when complex life began on Earth, this wave reached a cluster of galaxies near the constellation Bootes. The civilization began its work. Galaxy after galaxy went dark. 10,000 galaxies disappeared over millions of years, enclosed in spheres, their light shut off. Today, we observe the result, the Bootes void, a spherical region, 330 million light-years across containing only 60 visible galaxies. The other 9,940 galaxies are still there. They're just hidden, enclosed, invisible. The void isn't empty, it's occupied. The 60 visible galaxies are stragglers. Either the civilization hasn't reached them yet, or it deliberately left them visible for reasons we can't comprehend. They mark the boundary of the enclosed region, showing us where the work began or where it stopped. The void's perfect spherical shape makes sense in this model. The civilization expanded outward from a central point, enclosing galaxies in all directions at roughly equal rates. The sphere represents their domain, steadily growing as they extend their reach. This theory, sometimes called the transcension hypothesis, has prominent supporters. Some scientists argue we should take it seriously because it makes testable predictions. If the void contains Dyson spheres, it should emit infrared radiation at specific wavelengths. Deep infrared surveys should reveal point sources corresponding to enclosed galaxies. No such sources have been found. The void appears dark in infrared, just as it appears dark in visible light. If Dyson spheres exist there, they're radiating at wavelengths we haven't observed or using heat management methods that don't produce detectable signatures. The theory's timeline creates problems. 700 million years isn't enough time for a civilization to enclose 10,000 galaxies, even if they moved at close to light speed. Each galaxy requires massive construction efforts, billions of individual spheres, material harvested from countless solar systems, engineering on scales that dwarf anything we imagine. Perhaps the process began earlier than 700 million years ago. The light we see represents the void as it existed then. Maybe the civilization started work billions of years earlier. and what we observe is a snapshot of ongoing expansion. By now, in the void's current state, the entire region might be enclosed. This solves the timeline issue but creates another problem. If the civilization has been working for billions of years, why stop at the void's current boundaries? Why not continue expanding, enclosing the surrounding superclusters? Unless those superclusters represent the limit of their expansion, barriers they chose not to cross. The idea terrifies because it implies intent. Natural voids are accidents of cosmic structure formation. An artificial void is deliberate. Something chose to enclose those galaxies. Something with power beyond comprehension. Something that might still be there, watching, building, expanding. If we detected such a civilization, what would we do? Attempt contact? Hope they ignore us? Our galaxy sits 700 million light-years away, safely outside the void. But if they're still expanding, and they continue for another billion years, they might reach us. Most astronomers dismiss the Dyson sphere theory as wildly speculative. No evidence supports it. The void is more easily explained through natural processes, even if those processes are poorly understood. Invoking advanced aliens violates Occam's razor, the principle that simpler explanations are preferable, but a small minority keeps the theory alive. They point out that the void's strangeness demands explanation. If natural processes can't account for it, maybe we need to consider unnatural ones. The universe is old enough for advanced civilizations to exist. If they do, they would inevitably modify their environments on cosmic scales. The Bootes void could be our first glimpse of such modification. A megastructure so large it spans a significant fraction of the observable universe, built not for war or exploration, but simply for energy. A civilization harvesting the light of 10,000 galaxies, rendering them invisible, creating darkness where stars once shined. It probably isn't true. The theory requires too many assumptions, too many leaps, but it haunts researchers because it's possible, because nothing in known physics forbids it, because somewhere in the universe, on timescales longer than our civilization has existed, something like this could happen. And if it happened once, it could happen again, anywhere, everywhere. The universe might be filled with enclosed galaxies, invisible civilizations, megastructures beyond our detection. We would never know until the darkness reached us. Reality might be bigger than the universe. String theory, quantum mechanics, and cosmic inflation all suggest our universe exists within a larger structure called the multiverse. Countless other universes bubble off from eternal inflation, each with its own laws of physics, its own constants, its own history. We can't see them, we can't visit them, but occasionally, maybe, they leave traces. The Bootes void might be one of those traces, a scar where our universe brushed against another. Eternal inflation theory proposes that space inflates exponentially in most regions, but occasionally bubbles nucleate where inflation stops and normal expansion begins. Each bubble becomes a universe. These bubble universes expand inside the inflating background space, growing like soap bubbles in an infinite foam. Sometimes, bubbles collide. When they do, the collision releases enormous energy along the contact surface. This energy disrupts normal structure formation. Matter distribution gets distorted. The collision leaves a circular imprint on each universe, a region where physics briefly behaved differently during the universe's formation. A collision in the early universe, within the first few 100,000 years after the Big Bang, could create a circular void. The energy released would push matter away from the impact site. As the universe expanded, this pushed matter would form structures at the collision's edge. The center would remain empty, depleted by the collision's energy. The void's spherical shape fits this model perfectly. Collisions between spherical bubbles create circular contact regions. The surrounding superclusters could be matter compressed at the collision's edge, similar to how shock waves compress gas. The void's size and structure match predictions from collision simulations. The cosmic microwave background should show evidence of such collisions. The impact would create temperature patterns, specific signatures that differ from normal cosmic structure. Several research teams have searched for these signatures in background radiation data. Results are controversial. Some studies claim detection of circular patterns consistent with bubble collisions. Others argue these patterns result from statistical noise or analysis artifacts. The evidence isn't strong enough to convince most cosmologists, but it's not weak enough to dismiss entirely. The cold spot might be another collision signature. Its unusual size and temperature depression match some collision models better than standard void theories. If both the cold spot and Booty's void are collision signatures, we would have multiple examples, making the theory more plausible. Multiverse collisions would affect more than structure formation. They might alter physical constants slightly in the collision region. The strength of gravity, the mass of particles, the speed of light, all could vary microscopically. These variations would be nearly impossible to detect but could influence how galaxies formed and evolved in affected regions. Testing this requires comparing galaxies inside and outside the void. Do they have identical properties? Are star formation rates, chemical compositions, and evolutionary histories indistinguishable? Any systematic differences might indicate altered physics resulting from a collision. Current observations show no clear differences. Void galaxies appear normal by every measure. If a collision occurred, it didn't alter physics enough to leave detectable traces in galactic properties. This doesn't rule out collisions, but it constrains how violent they could have been. The multiverse theory is controversial. Many physicists consider it untestable speculation. We can't observe other universes directly. We can't create them in laboratories. Predictions are fuzzy, often allowing for wide ranges of outcomes that explain almost anything. Yet multiverse theory emerges naturally from well-tested physics. Inflation explains many observed properties of our universe. String theory requires extra dimensions and predicts multiple possible vacuum states. Quantum mechanics suggests reality branches continuously. All these theories point toward a multiverse, even though none prove it exists. If the multiverse is real, evidence should exist in our universe's structure. Collisions would leave fingerprints. Variations in physical constants might appear in different regions. The universe's overall geometry might reveal clues about the larger structure it inhabits. The Bootis void could be that evidence, a whisper from beyond our cosmic horizon, a hint that reality extends farther than telescopes can see. If confirmed, it would revolutionize physics and philosophy simultaneously. We would know we're not alone in the ultimate sense. Other universes exist, close enough to touch, leaving marks on our reality. But confirmation remains elusive. The void could be a collision signature. It could also be a natural structure formed through standard cosmology. Without stronger evidence, we can't distinguish between these possibilities. The multiverse remains a beautiful idea, lacking observational support. Some researchers argue we should keep searching, develop better theoretical models, make sharper predictions, collect more data. Eventually, if collisions occurred, we will find definitive evidence. The search continues, driven by the possibility that the Bootis void is our first glimpse of the multiverse. Others argue we're chasing phantoms. The void has a natural explanation we simply haven't discovered yet. Invoking multiverse collisions is premature, a leap beyond available evidence. We should exhaust conventional explanations before embracing exotic alternatives. The debate continues. The void remains mysterious. And somewhere in the mathematical possibilities of string theory and eternal inflation, the multiverse might be whispering secrets through the darkness. Gravity should be simple. Mass creates curvature in space-time. Objects follow that curvature. Einstein's equations describe this perfectly, verified by countless experiments. But measurements near the Bootis void show something strange. Galaxies move in ways that don't quite match predictions. The numbers are off by small amounts. Small enough to be errors, large enough to be troubling. Galaxies at the void's edge should follow specific velocity patterns. Gravity from surrounding superclusters should pull them away from the void. Dark energy should push them away from each other. The combination determines their motions precisely. We can calculate what those motions should be. Observations don't match calculations. Galaxies move slightly faster than predicted. The discrepancy is only a few percent, barely above measurement uncertainty. But it appears consistently across multiple observations using different instruments. Something is affecting these galaxies beyond what standard models include. One possibility is missing mass. Maybe the surrounding superclusters contain more matter than we detect. Additional dark matter could provide extra gravitational pull, explaining the higher velocities. Surveys have searched for this missing mass without finding it. Upper limits from gravitational lensing studies rule out enough hidden matter to explain the discrepancy. Modified gravity offers another explanation. Perhaps Einstein's equations need adjustment on cosmic scales. Several theories propose that gravity behaves differently across hundreds of millions of light years than it does in solar systems or even galaxy clusters. These modifications could explain both the void structure and the velocity anomalies. Testing modified gravity requires precise measurements across many voids. If gravity varies with scale, the effect should appear everywhere, not just in the Bootes void. Current data from other voids show mixed results. Some support modifications, others match Einstein's predictions perfectly. The picture remains unclear. Gravitational waves passing through the void might contribute. The universe is filled with gravitational waves from countless sources. Merging black holes, colliding neutron stars, even the cosmic microwave background has a gravitational wave component. These waves subtly affect galaxy motions as they pass. In normal space, gravitational waves from many directions average out, producing no net effect. In the void, with its unusual geometry and surrounding structure, waves might not average out completely. A preferred direction could emerge, biasing galaxy motion slightly. Calculating this effect precisely is mathematically challenging, but preliminary estimates suggest it's too small to explain observations. Dark matter distribution might be unusual. Standard models assume dark matter follows patterns predictable from cosmic structure formation. But dark matter doesn't interact with light or normal matter except through gravity. Its distribution could be more complex than we assume. If dark matter clumps in unexpected ways around the void, it would create gravitational effects that don't appear in standard calculations. Galaxy velocities would deviate from predictions. Mapping dark matter precisely enough to test this requires observation techniques we're still developing. The void itself might generate gravitational effects. Empty space in general relativity isn't truly empty. It has curvature, energy density, quantum fluctuations. A region as large as the Bootes void could have properties that affect how gravity propagates through it. This would be subtle, perhaps detectable, only in statistics of many galaxy motions. Some physicists propose the void acts as a gravitational lens in reverse. Normal lensing focuses light and strengthens gravitational effects. The void might defocus them, weakening gravity in its vicinity. This would make surrounding galaxies move differently than expected, appearing to move faster because they experience less gravitational restraint. The concept of gravitational defocusing is speculative. It requires properties of spacetime that aren't part of standard general relativity. Testing it demands observations precise enough to distinguish defocusing from other effects, and we're not there yet technologically. Quantum gravity effects might emerge at void scales. General relativity describes gravity as spacetime curvature. Quantum mechanics describes everything else. Combining them into quantum gravity has resisted solution for decades. But perhaps, at the largest scales, where space-time is most gently curved, quantum effects become visible. The void could be a natural laboratory for quantum gravity. Its extreme emptiness and enormous size might amplify effects too small to detect elsewhere. Galaxy motion anomalies might be the first observable quantum gravity phenomena. a hint of physics beyond both general relativity and quantum field theory. This idea excites theoretical physicists but frustrates observational astronomers. Quantum gravity predictions are vague. Different approaches to quantum gravity make different predictions. Without a complete theory, we can't calculate what effects should exist or how large they should be. We're searching for something without knowing what it looks like. The gravitational anomaly might not exist. Measurement errors, systematic biases, or incomplete data could produce apparent discrepancies that vanish with better observations. Many initial anomalies in astronomy disappear under closer scrutiny. This could be another, but some researchers believe it's real. Too many independent observations show similar effects. Too many different analysis methods reach similar conclusions. If the anomaly is real, it points to new physics. Either gravity works differently than we think, or something in the void affects gravitational interactions in ways we don't understand. Either possibility would be profound. Gravity is the best tested theory in physics. Finding deviations would shake physics to its foundations. It would mean our understanding of the universe's largest scales remains incomplete. The void would become more than a mystery. It would become a teacher, showing us where our theories fail. Every sphere has a center. The Bootes void, nearly perfectly spherical, has a center point 700 million light-years from Earth. What sits at that center? Standard theory says nothing. Empty space, maybe a few wandering atoms, quantum fluctuations. Nothing special, nothing worth noticing. But centers matter. Every structure forms around something. Galaxies form around dark matter concentrations. Stars form around collapsing gas cores. Even voids, if they form from expanding bubbles, have centers marking where expansion began. The void's center should tell us how it formed. Scientists have aimed instruments at that central region. Radio telescopes, infrared surveys, optical observations, X-ray satellites. They found nothing unusual, no massive object, no energy source, no anomaly. The void's center appears as empty as the rest of the void. More empty, even, because it's farthest from the surrounding galaxies. This absence is suspicious. If the void formed from gravitational processes pulling matter outward, something should remain at the center. The last wisps of gas unable to escape. A failed galaxy that never gathered enough material to ignite. Cosmic debris marking the void's origin point. Finding nothing suggests the void didn't form through gradual depletion. Some theories propose a primordial black hole sits at the center. These black holes would have formed in the early universe from quantum fluctuations long before stars existed. They could have any mass from microscopic to thousands of times our star's mass. A large primordial black hole could have consumed surrounding matter, creating the void. The problem is invisibility. Black holes should be detectable through gravitational effects on nearby objects. The void's center contains no nearby objects to be affected. A black hole could hide there, invisible because nothing gets close enough to betray its presence. But this seems contrived. Why would a black hole sit exactly at the void's center? Why would it create such symmetric structure? Others suggest an exotic object, a cosmic string passing through the void's center, a domain wall intersection, a relic from the universe's earliest moments when physics worked differently. These objects would have gravitational effects distinct from normal matter, potentially explaining the void's formation. Exotic objects remain hypothetical. We've never detected cosmic strings, domain walls, or any other topological defects from the early universe. Proposing they exist at the void's center explains one mystery by invoking another. It's unsatisfying scientifically. White holes present another possibility. These are theoretical time-reversed black holes. Where black holes pull everything in, white holes push everything out. They might have existed briefly in the early universe, creating expanding bubbles of space that pushed matter away. A white hole at the void's center could have created the observed structure, White holes are allowed by general relativity but probably don't exist. They're unstable, collapsing instantly under realistic conditions. Even if one formed, it would evaporate too quickly to create void-sized structures. The theory is mathematically interesting, but physically implausible. Naked singularities are singularities without event horizons. Black holes hide their singularities behind horizons, preventing us from seeing where physics breaks down. Naked singularities would be visible, exposed to observation. They're probably impossible, according to cosmic censorship conjecture, but if they exist, they would have bizarre gravitational properties. A naked singularity at the void's center would push matter away through effects we can barely calculate. It would create exactly the kind of symmetric structure we observe. It would be undetectable directly because singularities are point-like, infinitesimally small. It fits the observations perfectly. It also requires abandoning cosmic censorship, one of physics' fundamental assumptions. Without cosmic censorship, singularities could be common, scattered throughout the universe, wreaking havoc on space-time. We see no evidence for this. The void's singularity would have to be unique, which again seems contrived. Maybe the center contains nothing exotic. Maybe it's empty because that's what voids do. They empty out completely, leaving no remnant. The center is unremarkable because the entire void is unremarkable, just larger than we expected. But that doesn't satisfy curiosity. Humans want causes. We want origin points. A structure this large and this symmetric should have a cause, something that set it in motion. Finding nothing at the center feels incomplete, like reading a book missing its first chapter. The singularity question isn't really about what sits at the center. It's about what caused the void. If we understood the cause, we wouldn't need to wonder about the center. The fact that we keep wondering, keep proposing exotic objects and unlikely scenarios, reveals our uncertainty about the void's origin. Future observations might reveal something. Better instruments with higher sensitivity could detect faint objects current telescopes miss. Gravitational wave detectors might pick up signals from the void's center, revealing hidden masses. Neutrino telescopes could spot particles produced by exotic processes. Or we might find nothing. The center might be exactly what it appears. Empty space, unremarkable, holding no secrets. That would be its own kind of answer. It would tell us the void formed from large-scale structure processes, not from a central cause. The symmetry would be coincidence or consequence of cosmic inflation, not design. Either way, the question haunts researchers. What lies at the heart of the great nothing? Is it truly nothing, or are we missing something? The void keeps its secrets, 700 million light-years away, waiting for instruments sensitive enough to probe its deepest mysteries. After decades of study, thousands of observations, countless papers published and theories proposed, the Bootes void remains mysterious. We've learned much. We've measured its size, mapped its structure, tracked its expansion, but the fundamental questions remain unanswered. How did it form? Why is it so large? What does it tell us about the universe? We don't know if the void is unique. Sure, it's the largest nearby supervoid, but the universe is vast. Other voids might exist at greater distances, too far to detect clearly. Some might be even larger than the Bootes void. If supervoids are common, the void becomes an example of natural cosmic structure. If rare, it becomes an anomaly demanding special explanation. Current surveys can't answer this definitively. We've mapped millions of galaxies, but that's a tiny fraction of the universe. Most of cosmic space remains unobserved. Voids could hide everywhere, and we would never know until surveys extend farther and deeper. The void might be ordinary after all, we just lack perspective. We don't know the void's ultimate fate. Will it continue expanding forever, driven by dark energy? Will surrounding superclusters eventually halt its growth? Will galaxies fall into it from the edges, gradually filling it over trillions of years? Cosmological timescales dwarf human timescales. The void's evolution plays out over billions of years, we see a single snapshot of a story billions of years long. Models predict the void will keep expanding as long as dark energy dominates. Eventually, in the far future, when the universe has expanded so much that galaxies can no longer see each other, regions like the Booty's void will become the norm. The entire universe will be void-like, with isolated galaxies separated by unfathomable distances. The void gives us a preview of the cosmos's ultimate state. We don't know what happened in the first billion years. The void started forming early, possibly within a few billion years of the Big Bang. Observations of that epoch are difficult. Telescopes can peer back in time by observing distant objects, but looking back to when the void was forming requires seeing through the void itself, which blocks our view. The James Webb Space Telescope and future observatories might help. By studying galaxies behind the void, we can measure how light gets affected, passing through its structure at different epochs. This could reveal when the void reached its current size and how quickly it formed. We don't know if life exists in the void galaxies. 60 galaxies contain billions of stars each. Some fraction hosts planets. Some fraction of those planets might support life. But any civilization developing in a void galaxy would face unique challenges. Without nearby galaxies visible to naked eyes, astronomy would develop differently. Advanced technology would be necessary to detect other galaxies, maybe centuries later than it developed for us. Communication with potential neighbors would be impossible. Radio signals would take tens of millions of years to reach the nearest galaxy. Void civilizations would be profoundly isolated, possibly believing themselves alone in the universe until very recently in their history. We don't know if the void is expanding faster than predicted. Current measurements suggest it grows at rates consistent with uniform dark energy, but measurement uncertainties allow for small deviations. Future observations might reveal the void expanding slightly faster or slower than expected, indicating either dark energy variations or gravitational anomalies. This matters enormously for cosmology's future. Dark energy drives cosmic acceleration. If it varies by location or strength, the universe's fate becomes uncertain. Everything from the timeline of cosmic expansion to the possibility of future structure formation depends on dark energy's properties. We don't know if the void connects to other cosmic mysteries. The cold spot, dark flow, the axis of evil in the cosmic microwave background, all represent anomalies in cosmological observations. Some might relate to voids, others might be unconnected, or they might all point to the same underlying phenomenon we haven't discovered yet. Finding connections between different anomalies is how science progresses. A theory explaining multiple observations is stronger than one explaining just one. If someone proposed a mechanism that explained the void, the cold spot, and other anomalies simultaneously, it would revolutionize cosmology. We don't know if we're asking the right questions. Maybe the void isn't anomalous at all. Maybe our models are wrong in ways we haven't realized. Maybe the universe is fundamentally different than our theories predict, and the void is showing us that difference. Science advances through paradigm shifts. Copernicus showed us Earth isn't the universe's center. Einstein showed us space and time are malleable. Hubble showed us the universe is expanding. The void might herald another shift, forcing us to reimagine reality on the largest scales. Or maybe it's just an emptier than average region of space. Unusual but not mysterious. Interesting but not profound. The universe is vast and varied. Sometimes things are just less common than average without needing exotic explanations. The void might be cosmology's equivalent of a statistical outlier. Real, measurable, but ultimately mundane. We won't know until we know, until observations become precise enough to distinguish between possibilities, until theory advances enough to make clear predictions, until someone has the insight that makes everything click into place. The Booty's void waits 700 million light-years away. It has waited for 13 billion years already. It will wait billions more, patient, silent, empty, holding secrets we might never fully unravel. A monument to absence. A reminder that for everything we've learned about the universe, vast mysteries remain. 330 million light-years of darkness, 60 lonely galaxies, and questions that echo across the cosmos, unanswered.